Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is algebraic manipulation. Our objective is to review how one algebraically manipulates an expression to solve a desired property. This lecture operates under the presumption that viewers watch the DC Math lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. In the aforementioned lecture, we reviewed the order of operations, negative and fractional exponents, and the use of the scientific calculator. It might have taken a little effort on your part, but most likely you emerged from this lecture with a refreshed understanding and a deeper appreciation of these skills. If only the same thing could be said about algebraic manipulation. To be perfectly honest, a significant percentage of individuals truly suck at this skill and cannot algebraically manipulate their way out of a paper bag, even if I held the end of the bag open for them. Like it or not, I'm shoving you in that bag and you're going to have to fight your way out because algebraic manipulation is a necessary skill for the electrical circuit analysis series. But before I do, I'm asking you to heed the following general advice. 1. Have a goal and keep the goal in sight at all times. The goal is to isolate the desired unknown property on one side of the equality and all the knowns on the other. 2. Forget the numbers and the units until the final step. Only when you arrive at a final expression should you substitute in the numbers and the units. And finally, 3, follow the rules. You can't force a square piece into a round hole. Always maintain equality. Into the bag we go. During the course of your study, you'll often be presented with an equation in a particular form. An example might be Ohm's law, something we'll discuss at great length in the very near future, expressed as I equals V over R, where the concept of current is symbolically represented as an I and measured in units of amps, is equal to voltage, symbolically represented as a V, measured in the units of volts, divided by resistance, symbolically represented as an R, measured in units of ohms, kind of this funny shaped horseshoe thing. If you've got known voltage and known resistance, one simply divides voltage by resistance and obtains current in units of amps. For example, given a known voltage of, let's say, 14.3 volts across a 240 ohm resistor, an application of Ohm's law demonstrates one might expect roughly 59.6 milliamperes of current to travel through it. Too easy. An equation like this is a machine as complicated as an apple peeler. It has inputs, voltage and resistance. It performs some operation, voltage divided by resistance. It has an output, current. We explored this level of calculation in the aforementioned DC Math lecture, and this should be well within your ability level. Not all the time we were presented with such a perfect setup. Sometimes we know voltage and current, but not resistance, or maybe we know current and resistance, but not voltage. No problem. One can always algebraically manipulate a given equation to solve for unknown properties given known inputs. Allow me to demonstrate using Ohm's law. Let's say we know current I and resistance R, and want to use these properties to solve for voltage V. The goal of algebraic manipulation is to isolate all the knowns on one side of an equation and all the unknowns on the other. Given our present understanding of Ohm's law, known entities I and R need to be on one side of the equation and unknown quantity V on the other. One doesn't just move these quantities around without restriction, but rather one follows rules regarding their movement. The single most important rule being the equal sign. One can arrange and rearrange any equation in any fashion you wish. However, equality must be maintained at all times. That's the point of equations like Ohm's law. There exists a real observable relationship between these properties, and any upsetting of the equality means you're making things up. Equality must be maintained. Here's the general rules to maintaining equality. They all share a common trait. See if you can identify the shared trait. One can add any quantity you wish to one side of the equation. However, you must also add the same quantity to the other side of the equation. One can subtract any quantity you wish to one side of the equation. However, you must also subtract the same quantity to the other side of the equation. One can multiply one side of the equation by any quantity you wish. However, one must also multiply the other side of the equation by the same quantity. One can divide one side of the equation by any quantity you wish. However, you must also divide the other side of the equation by the same quantity. One can raise one side of the equation by any power you wish. However, you must also raise the other side of the equation by the same power. One can invert one side of the equation. However, you must also invert the other side of the equation. Have you figured out the pattern yet? For those of you who haven't, here it is. To maintain equality, one must do to one side what is done to the other. We need to isolate unknown property v on one side of the equation. As presently illustrated, it's being divided by r. What's the opposite of division? Multiplication. Multiply both sides by r. R cancels out on the right, and we're left with an equally valid permutation of Ohm's law, which states I times r equals v. One can substitute in known values for I and r and determine unknown quantity v. Other equally valid permutations of Ohm's law exist. For example, let's say we knew v and I and wanted to solve for unknown quantity r. We've got a couple different starting points. Let's begin with our second permutation of Ohm's law. As presently illustrated, we need to isolate the unknown property r on one side of the equation. R is presently being multiplied by I. What's the opposite of multiplication? Division. Divide both sides by I. I cancels out on the left, and we're left with yet another equally valid permutation of Ohm's law, which states R equals V over I. One can substitute in known values for V and I and determine unknown quantity R. Note, one needn't use the second permutation to arrive at the third, but rather proceed from first to third directly. Importantly, it should yield the same result. Allow me to demonstrate. Using the original statement of Ohm's law, we again need to isolate the unknown property R on one side of the equation and known properties V and I on the other. As presently illustrated, R is in the denominator. I do not like that. Let's invert both sides. Inversion means we flip both sides. We're left with 1 over I equals R over V. Unknown property R is being divided by V. What's the opposite of division? Multiplication. Multiply both sides by V. V cancels out on the right, and we're left with the identical permutation of Ohm's law, which states R equals V over I. One can substitute in known values for V and I and determine unknown property R. Note in all of these manipulations, I'm giving myself an indication of those steps I performed leading up to these answers. It might seem unnecessary given the simple expression, but trust me, in a more complicated expression, this is a great way of leaving yourself a trail to backtrack if you mess it up. While we're still looking at this simple three-variable expression, let me show you a great shortcut for algebraic manipulations of similar types of expressions. Consider the three properties central to Ohm's law, V, I, and R, illustrated inside a triangle. Let's say I is our property of interest. Cover it up. I is equal to V divided by R because V is over R. This is our original statement of Ohm's law. What if V was our property of interest? Cover it up. V is equal to I times R because I is next to R. This is the second permutation of Ohm's law. Similarly, what if R was our property of interest? Cover it up. R is equal to V divided by I because V is over I. This was our third permutation of Ohm's law. For simple three-variable expressions like Ohm's law, this is a lightning-fast means of algebraically manipulating equations to solve for the desired unknown property. Put your understanding of this concept to the test with this series of illustrated examples of the DC power equation, something we'll examine in greater detail in the near future. Given power, symbolically represented as P, measured in units of watts, is equal to voltage, symbolically represented as V, measured in units of volts, times current, symbolically represented as I, measured in units of amps. See if you can algebraically manipulate this equation to solve for V, given known inputs P and I. Similarly, see if you can algebraically manipulate this same equation to solve for unknown quantity I, given known P and V values. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given P equals V times I, an algebraic manipulation of this equation demonstrates that V is equal to P over I. Given known P and I values, one can solve for unknown V by dividing P by I. Similarly, an algebraic manipulation of the original or the second permutation demonstrates that I is equal to P over V. Given known P and V values, one can solve for unknown I by dividing P by V. That wasn't too hard, was it? Again, the triangle method works equally well here. Overlay P, V, and I in a triangle. Let's say P is our property of interest. Cover it up. P is equal to V times I because V is next to I. This was our original permutation of the DC power equation. What if V was our property of interest? Cover it up. V is equal to P divided by I because P is over I. Similarly, what if I was our property of interest? Cover it up. I is equal to P divided by V because P is over V. All right, let's turn up the heat. Not all the time we are presented with such simple expressions, and sometimes we need to synthesize two expressions into one. Case in point, Ohm's law, and the DC power equations. Thus far, we have three permutations of Ohm's law. V equals I times R, I equals V divided by R, and R equals V divided by I. Additionally, we have three permutations of the DC power equation. P equals V times I, V equals P divided by I, and finally I equals P divided by V. Given these six equations deal with the same properties, can we use them to divide other valid relationships between P, V, I, and R? Indeed we can. For example, given known V and known R, can we solve for unknown P? Consider one permutation of Ohm's law, which states I equals V over R, and a permutation of the DC power equation, which states P equals V times I. If I equals V over R, we can substitute V over R into the power equation, which yields V times V divided by R, which simplifies to P equals V squared divided by R. Let's say we wanted to solve for unknown P using the known quantities of I and R. We'll start with one permutation of Ohm's law, which states V equals I times R, and the original DC power equation, which states P equals V times I. If V equals I times R, one can substitute I times R in for V into the DC power equation such that P equals I times R times I, which is simplified such that P equals I squared times R. Let's put your understanding of this concept to the test with this series of illustrated example problems. Given three permutations of Ohm's law, the three original permutations of the DC power equations, and these two new permutations, solve for the desired unknown properties in terms of the indicated known properties. The first example is asking us to solve for R in terms of V and P. The second is also asking us to solve for R, but only in terms of I and P. The third problem is asking us to solve for I in terms of P and R. And finally, the last problem is asking us to solve for V in terms of P and R. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following results. Our first problem is asking us to solve for unknown quantity R in terms of known P and V values. There's multiple places to start. Perhaps the easiest jump off would be one of the newer permutations, where P equals V squared divided by R. Solve for R. R is in the denominator. I don't like this. Let's invert both sides. When we flip both sides, we're left with 1 over P equals R divided by V squared. Unknown property R is being divided by V squared. What's the opposite of division? Multiplication. Multiply both sides by V squared. V squared cancels out on the right, or we're left with R equals V squared divided by P. One can substitute in known values for V and P and determine unknown property R. Alternatively, one can begin with one permutation of Ohm's law, which states R equals V over I, and another permutation of the DC power formula, which states I equals P over V. If I is equal to P over V, one can substitute P over V in for I, which yields a rather ugly fraction, R is equal to V divided by P divided by V. We have got to clean this up. Follow my lead here. Division is the same thing as multiplication by the inverse. This is an extremely handy trick. For example, some quantity divided by 2 is the same thing as that same quantity times 1/2, i.e. the inverse of 2. Similarly, dividing something by 4 is equivalent to multiplying that same quantity by 1/4. It stands to conjecture dividing V by P over V is the same thing as multiplying V times the inverse of P over V. The inverse of P over V is V over P, so we're left with R equals V times V divided by P, which when simplified yields R equals V squared divided by P. Notably the same result we obtained earlier, albeit by more direct means. In the interest of time, I'll review the remaining results using the most direct method. Other methods should exist that ultimately yield the same answer, albeit with more or less work. The second problem is asking us to solve for unknown property R in terms of known properties I and P. I started with the equation P equals I squared times R. Divide both sides by I squared cancels out on the right, or we're left with R equals P divided by I squared. The third problem is asking us to solve for unknown quantity I in terms of known properties P and R. Again, I started with P equals I squared times R. Divide both sides by R. R cancels out on the right, and we're left with I squared equals P divided by R. This is not the answer to the problem. We need to solve for I. Take the square root of both sides. Ultimately, we're left with I equals square root of P divided by R. Note the terms P over R appear entirely underneath the square root operation. Finally, the last problem is asking us to solve for unknown property V in terms of known properties P and R. I started with P equals V squared divided by R. Multiply both sides by R. R cancels out on the right. We're left with V squared equals R times P. Again, this is not the answer to the problem. We're looking for unknown quantity V, not V squared. Square root both sides. We're left with V equals square root of R times P. Again, note that the term P times R appears entirely underneath the square root operation. Alright, now that we've got some experience algebraically manipulating simpler and slightly more complex expressions, let's try this set of illustrated example problems on for size. Be warned, some of these might be tough. Struggle with them though. Don't tap out too quick. For the purposes of this lecture, don't necessarily concern yourself too much with the concept these equations represent right now, but rather concentrate today on the process of algebraic manipulation. We'll explore these phenomena in greater detail in later lectures. Remember, your goal is to isolate the unknowns on one side of the equation and the knowns on the other. Equality must be maintained. Don't jam pieces together that don't fit. Any operation you perform on one side of the equation must be performed on the other. Given mechanical power equals T times N divided by 9.55, the first problem is asking us to solve for T in terms of mechanical power and N. And the second problem is asking us to solve for N in terms of mechanical power and T. The third problem is asking us to solve for unknown quantity N2 in terms of known properties T1, T2, and N1. And the fourth problem is asking us to solve for unknown property N1 in terms of known properties N2, T2, and T1. Now don't freak out about these subscripts. T1 is simply a means of differentiating it from T2. These are not mathematical operators. They're simply subscripts designed to identify certain properties. Given efficiency equals power out over power in, the fifth problem is asking us to solve for unknown property P out in terms of known properties P in and efficiency. And the sixth problem is asking us to solve for unknown property P in terms of known properties P out and efficiency. Given x sub L equals 2 pi times F times L, the seventh problem is asking us to solve for unknown property L in terms of known properties F and x sub L. Given x sub C equals 1 divided by 2 pi F times C, problem 8 is asking us to solve for unknown property C given known properties F and x sub C. Lastly, given a circle with area of pi times r squared, and the fact that diameter is 2 times the radius, problem 9 is asking us to solve for area in terms of diameter. And problem 10 is asking the reverse. Solve for diameter in terms of area. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features the rotating mechanical power formula, which states rotating mechanical power is equal to torque, T, times rotational speed, N, divided by 9.55. We're being asked to solve for unknown torque, given known mechanical power and known speed. Unknown property T is being multiplied by N and divided by 9.55. Multiply both sides by 9.55. 9.55 cancels out on the right. Divide both sides by N. N cancels out on the right. And we're left with T equals 9.55 times mechanical power divided by N. Our second problem is asking us to solve for unknown property N, given known T and mechanical power values. Multiply both sides by 9.55. 9.55 cancels out on the right. Divide both sides by T. T cancels out on the right. And we're left with N equals 9.55 times mechanical power divided by T. Our second problem involves gear ratios, where the number of teeth on gear 1 divided by the number of teeth on gear 2 is equal to the rotational speed of gear 2 divided by the rotational speed of gear 1. We're being asked to solve for unknown property N2, given known properties N1, T2, and T1. Given T1 over T2 equals N2 over N1, multiply both sides by N1, where N1 cancels out on the right, where we're left with unknown property N2 equal to N1 times T1 over T2. Our next problem is asking us to solve for unknown property N1, given known properties N2, T2, and T1. Again, given T1 over T2 equals N2 over N1, one may initiate this algebraic manipulation by inverting both sides. Multiply both sides by N2. N2 cancels out on the right, and we're left with N1 equals N2 times T2 divided by T1. Our next problem deals with the ratio of efficiency, or efficiency is equal to the power out, P out, divided by the power in, P in. It's perhaps easiest to set this up in a triangle format. We're first being asked to solve for unknown property P out given known properties P in and an efficiency. Solve for P out by covering up P out. P out is equal to P in times efficiency, because efficiency is side by side with P in. The next problem asks us to solve for P in given known properties P out and efficiency. Cover up P in. P in is equal to P out over efficiency, because P out is over efficiency. Our next problem demonstrates that x sub L is equal to 2 pi times F times L. We're being asked to solve for unknown property L in terms of the known properties F and x sub L. Again, don't freak out by the subscript. L is not a mathematical operator. It's simply a means of identifying property x. X sub L equals 2 pi times F times L. Unknown property L is being multiplied by 2 pi F. Divide both sides by 2 pi F. You can do this all at once or one at a time. 2 pi F cancels out on the right-hand side, and we're left with L equals x sub L divided by 2 pi F. Given x sub C is equal to 1 divided by 2 pi F C, we're being asked to solve for unknown property C in terms of known properties F and x sub C. Given x sub C equals 1 over 2 pi F C, perhaps the easiest way to start is to invert both sides, such that 1 over x sub C equals 2 pi F C. Unknown property C is being multiplied by 2 pi F. Dividing both sides by 2 pi F, we're left with a rather ugly fraction, 1 over x sub C divided by 2 pi F on the left-hand side. It's important to remember division is equal to multiplication times the inverse. What's the inverse of 2 pi F? The inverse is 1 over 2 pi F. So 1 over x sub C divided by 2 pi F is equivalent to 1 over x sub C times 1 divided by 2 pi F. 2 pi F cancels out on the far right-hand side, such that unknown property C is equal to 1 over 2 pi F times x sub C. Our next problem demonstrates that the area of a circle is equal to pi times the radius squared. Additionally, what we're aware is diameter is equal to 2 times the radius. We're being asked to solve for unknown property A in terms of known property D. With very little effort, it can be demonstrated radius is half of diameter. So R equals D divided by 2. Now, given our area expression, where area of a circle is equal to pi times radius squared, we can substitute D over 2 in for R, which yields area equals pi times D divided by 2 squared. Note the parentheses. D divided by 2 times D divided by 2 is D squared divided by 4, which some mathematical purists will rearrange such the constants appear together, such that area equals pi over 4 times D squared. Lastly, we're being asked to solve for unknown property D, given known property A. Given we previously demonstrated that A equals pi over 4 times D squared, multiply both sides by 4. 4 cancels out on the right. Divide both sides by pi. Pi cancels out on the right, leaving us D squared equals 4 times area divided by pi. This is not the answer we're looking for. This is solving for D squared. We need to solve for property D. Take the square root of both sides, which yields D equals square root 4 times area divided by pi, which some mathematical purists may take the square root of 4 and write this as 2 times the square root of area divided by pi. All right, that might have been a little tough for some of you. Again, keep in mind this general guidance about algebraic manipulation. Isolate unknowns on one side of the equation and all the knowns on the other. Follow the rules when doing so. Equality must be maintained at all times. Any operation performed on one side must also be performed on the other. Lastly, don't forget what you're solving for. Too often I've observed individuals struggling with this topic perform some operation one step only to undo it in the next. By annotating each step of the manipulation process, you could backtrack and correct any mistakes you may have made. Before we bring this lecture to a close, let me answer a burning question that might have been in the back of your mind since you first learned algebraic manipulation way back in grade school. That question being, why are we doing this? This deserves an answer because the larger purpose may not be readily apparent so early in this lecture series. Your math teacher's goal in high school really was to frustrate and humiliate you. My purpose in reviewing algebraic manipulation is because it's used on a very frequent basis. Given an accepted relationship between certain properties and known values, one can solve for unknown properties. A simple example. calculations can take the place of equipment. Given 4 volts across a 680 ohm resistor, what's the current through it? Given Ohm's law demonstrates that I equals V over R, 4 volts divided by 680 ohms yields roughly 5.9 milliamperes. If you know voltage and resistance, you don't have to use an ammeter to measure current. You can calculate it. A slightly more complicated example. Will the part work? Oftentimes, rated mechanical power and rated speed appear on a motor nameplate, but rated torque is unlisted. Does a 200-watt motor operating at 1720 RPM have enough torque to do the job? Given mechanical power is equal to torque times rotational speed divided by 9.55, we demonstrated via algebraic manipulation that torque equals mechanical power times 9.55 divided by rotational speed. Substituting in 200 watts and 1720 RPM demonstrates this motor is capable of producing roughly 1.1 newton meters of torque at the rated condition. Does the job require 1.1 newton meters of torque or less? You should be good. Does the job require more than 1.1 newton meters of torque? Go get a bigger motor. Here's yet another example. What part do I need? Let's say we need to find which capacitance value will provide 500 ohms of impedance at 60 hertz frequency. The capacitive impedance magnitude equals 1 over 2 pi times the frequency times the capacitance value. We demonstrated via algebraic manipulation that C equals 1 over 2 pi times F times X sub C. Substituting in the known values for X sub C and frequency demonstrates that a roughly 5.3 microfarad capacitor should do the trick. We'll examine many practical applications like this and more as we progress further into the electrical circuit analysis series. In conclusion, this lecture presented a review of algebraic manipulation. We learned algebraic manipulation is the process of rearranging an expression such that all unknown properties are on one side of an equal sign and all the known properties on the other, all the while maintaining equality. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.